Welcome everyone. Till now we have seen what is mobile IP, then how packets are delivered in mobile IP. During that packet delivery, we saw that home agent forwards the packet to care of address, that is foreign agent or mobile node, wherever it is, via a tunnel. So let's see what is tunneling and what is encapsulation, which is important from tunneling point of view. So in this video we will see first two types of encapsulation, IP in IP and minimal. So let's start with what is tunneling. Tunneling is a very simple concept. So in the IP packet delivery mechanism, which is used for forwarding packets between home agent and care of address. Now care of address can be at foreign agent or it can be at mobile node also. We know that. So during this packet forwarding, a virtual pipe, which is also known as tunnel or which is known as tunnel, is established for carrying data packets between home agent and COA. On your screen, you can see the example network, part of an example network carrying a tunnel where packet exchange between home agent and foreign agent are exchanged via tunnel. Okay, so it's nothing but a virtual pipe, so it's not physically present. Actually tunnel is nothing but a link established between home agent and foreign agent, assuming that foreign agent has a COA. So link establishment between home agent and foreign agent is nothing but a tunnel. But then what is, how it is different from normal link which are established between any two routers? Okay, so let's see that. So packets entering the tunnel are forwarded inside the tunnel and leave the tunnel unchanged. Okay, so when packets are entering into this tunnel, when they come out they remain unchanged, because in fixed network we have seen sometimes packets are fragmented during the transition. For example, in this case, if there is a tunnel between home agent and foreign agent, that might not be a single link. There may be some intermediate router also, because this packet forwarding is carried out through internet. So internet may have routers in between home agent and foreign agent. So in fixed network, if tunnel is not formed, then packets may be fragmented here. But in tunneling, packets are not fragmented. However they are entered, they will be leaving the tunnel endpoint in the same fashion, unchanged. Okay, so that is one key difference. So what is tunneling? Tunneling is simply nothing but sending a packet through tunnel. But this link established between home agent and foreign agent is different from normal link which is established in wireless media or wired media, because during this link or during this tunnel packets are encapsulated. So tunneling is a sending packet through a tunnel achieved by using encapsulation. Okay, so what is encapsulation? That is the latter part. We will see that tunnel is created by home agent. So when we are talking about tunneling, it is always created by home agent. So tunnel starting point is at home agent and tunnel end point is at the care of address, which may be at foreign agent or it may be at mobile node also. So in case of care of address at mobile node, tunnel will exist between home agent to mobile node. Okay, so what is encapsulation? That is the next question, because tunnel cannot be formed without encapsulation. Encapsulation we have seen previously in the OSI model also, where we have seen it. Let's see that. So what is encapsulation? It is the mechanism of taking a packet consisting of a header and data and putting it into a data part of a new packet. We know that every packet consists of two parts, header and data. So taking a packet consisting of header and data and put it inside data part of a new packet. So this will be my data part of a new packet. It will also have a header. So this process of putting one packet inside the another packet is known as encapsulation. So we have seen this concept in OSI model also, or in fixed networks also. The reverse operation, taking packet out of the data part of another packet, is called as decapsulation. Both these encapsulation and decapsulation are typically performed when packets are transferred from higher protocol layer to lower layer, or from lower to higher layer respectively. So just as I said, we have seen this in the computer networks or fixed networks also, where we have different layers like physical layer, data link layer, network layer, transport layer. So network layer, we have a packet. Now it is given to higher layers by adding a header to it. So this is nothing but encapsulation. When it goes to the transport layer, it is inserted into a data part of a TCP segment. Okay, so here at network layer also we have a header and data. We put it inside a data part of a segment, attach a header. Now again this is put inside some, let's say, session layer, is the data part of a session layer packet format, and so on. Or decapsulation means when transport layer receives a packet from higher layers, it takes out its own header, so it vanishes and gives out only data part to the network layer. So network layer has only a data part which consists of header of network layer and data part of the packet. So it takes out the header part again and forwards it to the data link layer. Again at data link layer there will be again header and data part, which is a forming data part of a network layer. Same thing is done, header part is removed, given to the physical layer. So this mechanism we have already seen in the fixed network. Then what is the difference? In fixed layers or in OSI model, this encapsulation and decapsulation happens between two different layers, whereas in mobile IP, these functions are used within the same layer. So whatever we are doing, that is encapsulation or decapsulation, everything will happen at the network layer, both encapsulation and decapsulation. Higher layers are not involved, only network layer is involved. Okay, so let's see the types of, or before seeing the types, let's see the mechanism. Actually the mechanism is shown in figure and describe exactly what home agent at the tunnel entry does. So as you can see, home agent takes the original packet, which is shown here. This is original packet. I will denote it as a OP, which consists of original IP header, assuming IP network layer, that means IP packet, and original data. Now in this packet, source address will be correspondent node and destination address will be mobile node. Now this original packet is put into the data part of the new packet, you can see here. So this is new packet, I am denoting as a NP, which will have a new IP header in such way that packet is routed to the COA. Now this header will contain source address of a home agent and destination address COA, because this is carried from home agent to the COA. Okay, so this is the resultant packet, which consists of two headers, outer header, inner header, and data. Okay, so this is how encapsulation is done. So let's see how, or different types of encapsulation. So encapsulation in mobile IP, specifically we are talking about mobile IP, not about fixed networks now. It has three types: IP in IP encapsulation, minimal encapsulation, and GRE. Here it should be AND. That is the third type, generic routing encapsulation. GRE stands for that. So let's see the first type, IP in IP. It is the most basic type of encapsulation, and it is well known and most followed type of encapsulation. So encapsulation of one IP packet into another IP packet as a payload is known as IP in IP encapsulation. So one IP into another IP means what? Either IP version 4 into IP version 4 or IP version 6 into IP version 4, which is called as 6 bone. These are the types of IP in IP encapsulation. Now, as this is the most basic and simplest form of encapsulation, this is the mandatory type for mobile IP as specified by RFC 2003. Okay, so if you are going to implement a mobile IP, the minimum requirement is you should be able to implement IP in IP encapsulation. Other types, these are optional, but IP in IP is a mandatory one. So on your screen you can see a packet which is using the IP and IP encapsulation. You can see there are two headers. First one, this is the outer header, outer IP header, followed by inner IP header up to this part, and then below that there is a payload, that is data part. Payload is nothing but your data part. So outer IP followed by inner IP followed by data part, that is payload. Okay, so that is IP in IP encapsulation. So let's see the fields of this packet format in IP in IP. We have studied IP Internet Protocol version 4. Obviously, we are considering version 4 of here for discussion. So we have studied that in the previous semesters. So let's revise that and see how which fields are changed for IP in IP encapsulation. Now, first field for IP header is version field. It is 4 for IP version 4, 4 in decimal. So in binary it will be 0100. So there are 4 bits. Then followed by a field called as internet header length, that is IHL. It tells you the length of outer header in 32-bit words. In IP version 4 packet format, IHL represent length of a header. Now in this mobile IP, IP in IP, IHL represents length of header of outer part, that is outer header. So in 32-bit words, that is the difference. The next field is a DS or TOS field. When IP was originally invented, that is IP version 4 protocol was originally invented, this field was called as TOS, that is type of service. Later on it was modified and upgraded for different reasons. At some time it was called as a DS, that is differential service. Now latest version calls it as a DSCP, differential service code point. Okay, now what is type of service? Now we send different types of data like audio, text, image, video. So different type of data require different requirements or push different requirements onto the network. For example, a text may require minimum bandwidth. It will not require large bandwidth because it is having a very small size. And a text is not a live data. That means even if it is delayed by a certain period, we will still receive the information. But video, if you are transmitting, then it is time dependent, that is real time data. Real time data. So it is dependent on time interval, how quickly the data can be reached towards the destination. So it requires higher bandwidth, higher throughput, lower delay. So different QoS parameter for different type of data. So TOS field or type of service, or in this case DS field, indicates what type of data is included in this particular packet. Now why that is important? Because based on this field, routers are chosen for routing. So if you want a higher bandwidth for your delivery of a data, then you will choose a router which provides a better throughput, better bandwidth and lower delay. If you are transmitting a text, then you can go for cheaper route towards the destination. Cheaper in terms of it will not be providing any large bandwidth, it may not be very costly. Costly means in terms of delivery of data in time, it may be delayed also. So it will be very cheap in the that context. So depending on type of service we are choosing routers, and that's why this field is important for networks nowadays. Then next field is a length field. Now this length is different from IHL. This length covers the complete encapsulated packet. Means what? In IP version 4, length field indicates length of a total header. Sorry, length of a total packet, not header. IHL represents length of a total header. Now length field indicates length of a total packet. Now in this case, total packet is a total encapsulated packet. For outer header, length indicates length in total out encapsulated packet. The next three fields are similar to IP version 4 functioning. So they are copied. They have no special meaning for mobile IP. Like IP identification, it is used for identifying whether it is an entire packet, sequence number it may be called as. So it is important from receiver point of view whether they are receiving packets in correct order or not. For that can be useful. Sequence number is present in TCP, not in IP, but it works similar to that way. Then there are flags. Flags indicate whether this packet is fragmented or not. There are three flags. One is 0, D and M. D means don't fragment, M means more fragment. So if M is 1, this packet is fragmented. D is 1, that means this packet should not be fragmented. So fragment offset, if packet is fragmented, the offset from the original packet is mentioned in fragment offset, that is part, sixth part or seventh part or first part, that is mentioned in the fragment offset. Then next field is a TTL. Now TTL denotes, this is the TTL field. TTL stands for time to live. It denotes time in seconds within which packet must be delivered. This is important in order to avoid looping in the network. If TTL is infinity, packet will keep on circulating between the network. So to avoid this, TTL is mentioned. Now in IP version 4, TTL should be kept high enough so that packet will reach at least COA. Okay, so doesn't matter if there is multiple routers in between home agent and foreign agent. If home agent and foreign agent has multiple routers in between them, TTL will be always equal to 1. That means these three routers are considered as a single hop. TTL also called as a hop count. So these all routers will be called as a single hop. So this is to make sure, or this is important from this point of view, that your mobile node is just a one hop away from the home network. So it appears as if you are connected to home network. So that's why TTL field is very important. So this tunneling is kept hidden from the other part of a network. The next field denotes layer 4 protocol. In this case, for outer header, layer 4 protocol includes a code for IP in IP encapsulation. So it denotes the type of protocol used inside the payload part. So the payload part of outer header is this part. This is a payload of outer header. So what is the payload part? It is a IP version 4 packet again. So that's why here it is mentioned as IP in IP. Then there is IP checksum, which is calculated as usual. Checksum is calculated for the header part. This is used for detection of errors. So checksum is calculated for header part to detect if there are any errors at the receiver. It will be calculated again and matched with the original checksum, and then it will be decided whether packet was contaminated or not. Then next two fields are source address and destination address. as you can see, source address and destination address. Source address, as this is the outer header which is created by home agent, in this case source address will be IP address of home agent, and destination address is a foreign agent or COA, so destination address will be care of address. If there are no options, outer header is finished. Now next is inner header. Okay, so let's see what is the content of inner header. Now if you observe, inner header carries similar fields to the outer header with slight differences. Inner header remains almost unchanged during encapsulation, thus showing the original CN and MN as a source and destination address. Now inner header is actually a packet sent from the correspondent node. So correspondent node, if it is sending the packet, its source address will be CN's address and destination address will be mobile node's IP address, original, not COA. Okay, so COA is not mentioned in the inner header. So that is inner header, which carries almost every field similar to the outer header. The change is in TTL and layer 4 protocol. Okay, now length field will be also length of a head entire packet for only the inner part. Then TTL field, which is decremented by 1. This means that, as I said, in this case TTL is only equal to 1. In outer case it may be high enough to reach a care of address, so you can be keeping it as a 2 or 3 for outer header. TTL can be 2, 3, 4, anything for outer header, but for inner header TTL should be always equal to 1 to indicate that mobile node is just a one hop away from the home agent. Okay, this is very important feature of tunneling, as it allows mobile node to behave as if it is attached to the home network even if it is in the foreign network. No matter how many real hops the packet has to take in the tunnel, as I said, between home agent to foreign agent, there may be multiple hops due to different routers present in the internet. There may be multiple hops, but TTL will remain 1, as I said previously also, to hide the tunneling part from the rest of the network and to make mobile node feel as if it is still connected to the home network. Okay, so these are the changes. The layer 4 protocol, it will be including type of protocol included in the payload part. So since this is at network layer, the next layer will be transport layer. So type of protocol will be TCP in this case, because TCP or UDP, that will be the type of protocol, because payload part contains TCP segment or UDP segment, whichever it is. And after that, checksum as usual calculated for inner header, source address, destination address, if there are no options, followed by actual data. Okay, so finally payload follows the two headers. So this is regarding IP and IP encapsulation, which is the basic part. Now if you observe, there are so many fields that are repeated, like version, IHL, DSTOS, length is not repeated but still it is present, flags, fragment offset, IP identification, these are the fields which are repeated. So why we are sending the repetitive information? So that is another question. So we are wasting our bandwidth because size of packet will increase because of this repetitive information. In terms of one packet, that not may be substantial, but size of packet increases considerably if there are so many packets available in the network which are going through the tunnel. So it is consuming too much bandwidth. So that's why the next encapsulation technique is developed, that is minimal encapsulation. Now minimal encapsulation avoids repetition of identical fields like TTL, IHL, version, DS and so on. So similar to IP and IP, outer header is same as that of the IP and IP. Only thing that is changing is layer 4 protocol. Here the code will be 55 to indicate minimum encapsulation packet is inside the data part. Okay, apart from that all other fields are same, only layer 4 protocol field is modified to indicate the minimal encapsulation. So in the data part of outer packet we have a minimal encapsulated packet. So what is that? Let's see that. Only but this type of encapsulation is only applicable for non-fragmented packets. So if your packet is fragmented into different small packets, then minimal will not work for that, because those fields are fragment fields are removed in the next or minimal encapsulated packet. So if you see the inner part of a packet, that is inner header plus data, several fields are removed. The field type version IHL, DST, OSD are removed. The first field is a layer 4 protocol, which is indicating which type of protocol is present or which type of packet is present inside the payload. As usual it is TCP or UDP, just like in the IP in IP encapsulation. Next bit is a S bit, which indicates whether original sender address is mentioned or not mentioned. Usually it is mentioned, because not mentioning the source of a packet is not an option usually. So if S is equal to 1, the original sender's IP address is mentioned in the header, otherwise it is not mentioned. If S is equal to 0, then original sender IP address is not mentioned, but this happens rarely. Next few bits are reserved. After that IP checksum, which is same to the previous technique, calculating checksum of header part, inner header part. Then source address, in the minimal encapsulation packet, first it is a destination address, because that is mandatory. So destination address is IP address of mobile node, similar to IP in IP. And after destination address, the next field is a source address. Now if you compare this with IP in IP encapsulation, these fields are changing their position. In IP, source address was first and then there was a destination address. In minimal encapsulation, destination address is first and then there is a source address. That is the change. Why? Because in minimal encapsulation, source address is optional. If S is 0, source address will not be present. And if there are no options, directly payload will start after the destination address. But if S is equal to 1, source address will be present, and that's why it is included after destination address, and after that payload starts. Okay, so there, as you can see, there is no room for fragmentation for inner packet. So this is not the same packet which was sent by the correspondent node. It has been modified in its header, not the data part. Data part is kept as it is, header is changed, repetitive fields are removed, and new header is created called as a minimal encapsulated header, and it is inserted into the outer header, outer packet. Okay, so this is about minimal encapsulation. So we have seen two types of encapsulation in this video. In the next video we will see the next type, that is GRE. That's all for today. Thank you.